Hello, everyone. Thank you for joining us for today's webinar. This session is part of the Passive House and All Electric Homes Training and Workforce Development Initiative, brought to you by the sponsors of MassSave. All the trainings in this series are recorded and posted to the MassSave YouTube channel, so you can revisit those and share them throughout your networks. Next slide, Jared. MassSave is a collaborative of Massachusetts electric and natural gas utilities and energy efficiency service providers, also known as the sponsors, helping residents, businesses, and communities of the Commonwealth save energy and money by improving the energy efficiency of our buildings. As part of this training initiative, the sponsors offer a 50% cost reimbursement for individuals pursuing professional accreditations for either Passive House or Energy Star. Once you have successfully completed your certification course, you can fill out the reimbursement application found on our website and submit it to us for incentive processing. Next slide, Jared. The sponsors also offer robust incentives to homeowners, builders, and developers who incorporate energy efficiency upgrades into their design and build high-performance all-electric homes. To qualify, single-family homes or buildings with 1 to 4 units must have heat pumps for space conditioning and electric appliances for water heating, cooking, and clothes drying. Homes can qualify for incentives through one of 3 eligible performance tiers, which include a base tier for homes that exceed the building code, as well as tiers for Energy Star Next Gen and Passive House certification. Incentives start at $7,500 a home and also feature innovative market transformation adders, which are designed to encourage participants to pursue additional national certifications for their homes and to incorporate emerging equipment technology to drive higher building performance and enhance occupant comfort. Next slide. For multifamily buildings, the performance tiers and incentive structure is similar to that for single family, with the biggest difference being that multifamily buildings are allowed to have fossil fuel domestic hot water while remaining eligible for incentives. Please note that the program defines low-rise buildings as having 3 stories or less, while high-rise buildings have 4 stories or more, or any multifamily building that has centrally metered utilities for the tenants. There are some slight differences in the per unit incentives for low rise versus high rise, as you can see in the chart. And lastly, there are some additional market transformation adders for multifamily buildings, including more options for heat pump water heating equipment, as well as incentives for whole building air infiltration testing. If you have questions about these incentives, don't hesitate to contact us at the addresses shown on the slides. And for questions throughout today's session, you can use the questions drop down in the GoToWebinar control panel, and I will relay them to our speaker. And so to introduce today's speaker, Jared Blum is a senior architectural representative for Alpen High Performance Products with over 25 years of experience in the window industry. Over the past 8 years, he's worked closely with the architectural community, specializing in performance and integration of window systems in a broad range of projects, from new construction multifamily to historic preservation projects. So with that, I will turn it over to Jared. Jared, welcome. Thank you for joining us today.
Yeah, thank you so much, Keegan. Appreciate the introduction and being part of today's event. Welcome, everybody. Again, my name is Jared Blum. And the presentation that we have today is really focused on high performance glazing technologies. If we do have any architects in today's audience, this can also qualify you for 1 learning unit for the AIA. And if you would like to take advantage of that, I'm sure we can gather your information and make sure you get credit for that. I'm sure I can work with Keegan for that submittals. So I would suggest go ahead and put your information into the chat or directly back with Keegan, and we can certainly make sure you get those credits. So today's discussion is really brought through a lot of evolving energy codes that we're seeing, especially in Massachusetts, but certainly throughout the country. Massachusetts has really led the charge in code adoption and for higher performance standards. And now we see Passive House being even included in those in some of those multifamily projects, and along with other advancements in the residential standards. And so that brings about a lot of difficulties when it comes to designing and constructing higher performing buildings. So, and windows are certainly a very important part of the overall performance of a building. So for today's discussion points, we're going to spend a couple minutes talking about the overall impact that glazing has on the overall total wall performance. And then we'll dive into points 2 and 3 for a little bit, talking about the fundamentals of insulating glass and traditional glazing technologies, how glass performs and how we measure that. And then finally, we'll wrap up with identifying and also evaluating some emerging technologies in high performance glazing. And along with that comes a little bit of defining what high performance really is. So now there is a noted physicist, American physicist, Amory Lovins. He has written energy policy for many, many decades. He's also the co-founder of the Rocky Mountain Institute, and he was several years ago noted in stating that all of the energy pumped through the Alaska pipeline each year literally goes out of America's windows. And that's really a testament to how underperforming today's window stock in our building stock is, between still many single pane windows that are employed in a lot of commercial buildings. A lot of our older homes still have single pane windows, and they can be covered up with storm windows sometimes, but this even extends to dual pane windows that still do leak out a lot of energy. And if we look at a standard residential home that might have roughly 8% of the building envelope is glazing or windows, that 8% of the glazing area of the house contributes to about 45% of the heat transfer through the building. So it's a huge impact that the windows have on the overall performance of a house or a building. And so here's a little pop quiz, just to start off, and I'm giving you the formula right there at the top. If anyone has a calculator close by, feel free to grab it. But here's just one scenario to run by you. And if we were to have a wall insulation of R20, which is pretty common, especially in recent years, and an overall glazing area of about 50%, with windows that perform to U factor of 0.30, what would you guess is the overall effective R value of that entire wall? And I'll just give you a couple seconds to think about it. Is it 8.9? Is it 5.7? Or is it 14.4? Well, the answer is overall performance of that wall would be roughly 5.7. Now, this calculation is a very rudimentary calculation. It doesn't factor in for thermal bridging or imperfections in the walls, air sealing, anything like that. So it's not meant to be a substitute for much more sophisticated modeling software systems, but it does give us an idea of the overall impact that windows play on our overall wall performance. Now, say we wanted to improve that wall performance. Well, there's a couple options that we have. And actually, just backing up, so this wall assembly is very, very common to us with R20 insulation, roughly 0.30 U factors, and it might look something like this right there. But if we wanted to improve that, we have a couple options available to us, and one of which is just increasing insulation on the outside. And increasing insulation from R20 to R40 is not an easy thing. Many times that stud cavity is already filled with insulation. So that means adding extra insulation to the outside of the sheathing of the wall. And so that brings out a lot of other additional detailing. In addition to more materials, We have added strapping. We have to start thinking about rain screen detailing on these, and integrating that window when we're looking at the windows. Might mean boxing out for structural stability of the windows and added flashing details all throughout that assembly. So this adds more attention to the details for the installation and more materials. If we added that extra insulation and kept everything else the same with a 50% glazing ratio and the same windows at a U factor of 0.30, our added benefit from the baseline would be an additional 8% gain. So we're going up to an overall value of 6.2 on that. Another strategy that we might think about doing is improving just the windows. So starting with an R20 insulation within our walls. So we're going back to the baseline and the same glazing area of 50%, but now going from windows that perform to 0.30 down to 0.20. So this is a better performing window, going from roughly an R3 window to an R5 window on this. And the return is much more substantial. So now we're getting roughly an overall wall performance of about an R8. And in other terms, about a 40% gain from our baseline. So if we simply just improve the windows rather than the added insulation on the outside, we get a much easier, faster benefit from that. Now, obviously, if we were to combine both of those strategies, we get even better performance in the walls. So now 50% glazing ratio is pretty quite a lot, but as architectural trends, especially in residential construction, more modern homes are becoming more popular, and what we're looking for, many homeowners are looking for, is more glass and more connection to the outdoor environment. So what we're talking about is more, as energy codes continue to increase, we have a couple different options available to us. We can either shrink down the glazing or improve the overall performance of the wall by improving the windows to give you more architectural freedom. Now, 50% glazing ratio is pretty high. If you were to look at other glazing ratios, starting at 10% glazing here, you can see that the bottom line right here represents an R20 insulation ratings. Middle line represents R30 insulation, and the top line here represents R40 insulation in the walls. And the bottom x-axis here represents various U factors for windows, working from lower performing up on the left and higher performing on the right here. And we can see overall how that gets plotted out with 10% glazing ratio. The blue vertical bar that you see on this represents where we are today for Energy Star standards for windows and doors. So there is a bit of a range. We'll take a look at that in the coming slides. But you can see with lower insulation, R20 insulation, that line is pretty linear. But as we start to combine higher insulation levels along with higher performing windows, the return gets more pronounced or more exponential as you work your way into higher performing systems, such as over here on the right-hand side. Now, if we were to look at other glazing ratios for total wall performance, you can see how these lines get more and more pronounced as we build our building envelope with more and more glass. We're relying on the glazing to do the work for the insulation layers on our buildings here. And so let's take a step back and take a look at how heat transfers just very quickly here through a window assembly. And we'll use this information later on to help identify higher performing glazing systems. So the goal here is to, how do we keep our glass area on the walls without sacrificing performance? So heat transfer happens three different ways, and we're really going back to 5th grade science on this right here. So when we're talking about conduction, we're really just talking about the physical transfer of heat through the physical contact of materials, and that can happen many times at the frame and the sash components, even at the edge of the glass right here. So at where the glass comes in contact with the spacers, and then the extra pane of glass, that's where the conduction happens. For convection, that's where you see these blue and yellow loops right here. Now, convection can happen both on the inside living space and to the outside of the window, but it does happen within the air spaces of windows. So between the panes of glass, convective loops can happen there. When we have a cold winter night, the heat rises. So when this pane of glass gets cold, that cold air will drop down and force the warm air to come up within that airspace, and that starts the convective loops within there. And then finally, radiation is really just the radiation from moving through the windows themselves, and that's where many window companies will employ low-E coatings to counter that effect. We'll get into each of these a little bit more in the coming slides as well. But if you're to look at the overall performance of different components within windows, it's really broken down into 3 different main categories. The first, the center of glass, is the largest component that affects the overall performance of a window. Roughly 60 to 80% of the overall performance of a window comes from the glass. That's because it takes up the largest amount of area, and it actually happens to be the best performing component of a window system. The edge of glass takes up a smaller percentage, and that's roughly 10 to 20%. And there's a wide range of performance values that edge of glass can come from. And then finally, the frame system itself takes up about 10 to 30% of the overall performance of a window. And there's, as we all know, there's many different frame systems ranging from vinyl to fiberglass to wood and aluminum windows out there. All of those different frame systems perform differently. So this is just a little snapshot on overall frame performance. So obviously, as we look at this here, the largest opportunity to increase the performance of a window is the glass. Right here, we'll take a look at some other strategies for these 2 other here in the coming slides as well. So just to refresh a little bit on the overall how windows are measured, there is a standard published by the North American Fenestration Standard that requires most windows to be labeled with something like what's shown on your screen right now. This is many times referred to the NFRC sticker, but it does have several different areas that windows are measured in. So we'll just review those very briefly here. The first, and many times the most important indicator of performance, is the U factor. And we can see that listed right here in the top left corner. And the U factor is really a measure of how much heat energy is moving from inside to outside, or escaping through the window system in wintertime conditions. So it's taking at 0 degrees on the outside and assuming 70 degrees on the inside. And it's really a measure of how much heat escapes through that window system. This doesn't account for air sealing or anything like that. Really just a measure of the total window performance, including the frame, the glass, and the seals themselves. So because it's a measure of how much energy is lost, the lower the number, the better performing the window is. It also happens to be the direct inverse of the R value as well. So if we were to have a U factor of 0.20, that would equate to an R5 window, total window performance. It's also good to note that when we're looking at U factors, to identify if it's the center of glass that we're evaluating or if it's the total unit performance. The total unit performance will give you a better indication of the overall window assembly. The next measurement here is the solar heat gain coefficient, and that's shown right next to the U factor. And this is really just a measure of how much of the sun's radiation or heat comes from the outside to the inside. So unlike the U factor, this is more relevant to various different climate zones right here. So southern climate zones such as Florida, Texas, they want to block out as much solar heat gain as they can. Whereas as you work your way into northern climate zones, that's where some buildings or some homes can take advantage of that passive heating through the windows, especially in passive house construction. So it's not always it's not a straight rule that the lower the number, the better. It's really climate specific for the solar heat gain coefficient. Visible light transmission is more of a measurement of how much light is coming through that window assembly, including the frame area. Now, this doesn't always directly impact the energy efficiency of the window, but this can impact the energy efficiency of a home as we allow more light to come into the space. That reduces the need to turn on extra lighting, additional lighting to the inside. So this doesn't always have a direct measurement of the window's energy efficiency. Now we're going to skip over air leakage because today's performance is really focusing on the glazing performance, but just know that the lower the air leakage of a window, generally the better on that. And then finally, the condensation resistance here is taking at those same wintertime conditions, so 0 degrees on the outside, 70 degrees on the inside, and we start to think about the humidity levels that are playing on these right here. So high humidity on the inside, low humidity on the outside. And the higher the number that we have for condensation resistance, the better performing that window is. So, and when we're talking about condensation, we're really talking about the room side condensation right here, what develops on the room side surface of the glass. Now, this is an indicator of the overall performance of the window, how well it insulates from the frame systems to the glazing systems and the spacers within those glazing systems as well. So we'll identify several different ways to improve all of these numbers later in this presentation. If we look at over time here on the left-hand side, we can identify various traditional glazing solutions here, starting with single pane glass. And the movement really here was really kicked off in the 1970s energy crisis, where price of oil skyrocketed, which brought about new technologies in windows. First starting with double pane glass and then double pane low E windows. And triple pane windows have been on the market for some time. These are US adoption rates right here. So we really haven't seen much adoption of triple pane windows. Part of that is the added cost. Another part of that is they really haven't been needed from a code compliance standpoint until recently. And so we'll take a look at that. But most of the time, most of all the windows for code compliance today, we've been able to satisfy code by dual pane insulated glass that has low E coatings applied to it, argon fill, and the various low E coatings. And most recently, we've seen low E coatings applied to surface 2. This is the room sides facing surface of the outside sheet of glass. And now we see some low E coatings applied to surface 4. So this is now the interior facing surface of the glass. And so this is a low E coating that's applied to the inside surface of the glass. You can touch it, you can clean that low E coating. And what happens with this technology is it reflects the heat back to the inside of, back to the inside, creating a lower U factor. Now, because it's reflecting heat back to the inside, that heat does not have a way to warm this, the perimeter seals here, which causes those seals to actually get cold from the outside during wintertime conditions, especially on those really cold nights. And because that's getting cold right here, you have a higher likelihood of condensation with this solution, condensation building up many times at the bottom of the glass right here. And long-term condensation can lead to more problems down the road, such as mold buildup, and other problems. Now, if we were to think about various standards for high performance, what do we consider as high performance? Energy Star has always been one indicator of higher performance, meaning higher than code anyway. And we don't have to look too far back in history to see the advancement of Energy Star compliance in Windows. And so if we were to look at first the solar heat gain coefficient, you do see some evolution through these different versions here. But the bigger factor here is the U factors have really ratcheted up. Going back to as recently as 10 years ago, Energy Star was noted to be as high as 0.30, which we saw in the earlier slides. 6.0, we saw Energy Star creep up to 0.27, and now from a prescriptive standpoint, it's all the way up to 0.22. And this is really marking a point in history where once we go beyond 0.25, 0.24, this is really the point in which dual pane windows can really top out and what they can really achieve for performance. So as we look at higher performing window systems here, 0.23, 0.22, this is really the tipping point where we need to go from dual pane to triple pane windows in this range here. And we all know that Energy Star 8.0 is already being drafted right now. And I'm not sure exactly where that's going, but we all know the trend is going towards higher efficient window systems on these. Along with that, we see more code adoption. First, obviously in Massachusetts, we have the stretch codes and now the specialized stretch codes. I mentioned earlier that Massachusetts led the way in the country, and now we see over 26 states and territories who have also either adopted their own version of stretch codes or actively using the Massachusetts model as their next version of stretch codes as well. So we're seeing rapid adoption nationwide for these stretch codes. Even if we look to our neighbors to the north in Canada, they have aspirational goals for residential windows starting just next year in a couple months, that all residential windows will need to perform to a U factor of 0.21. That's an advancement from where they are now. And then in just 5 short years, that makes a big jump all the way up to 0.14 for the windows. So those earlier charts that we saw for overall glazing to wall ratio showed higher performing window systems. And that's the direction that certainly Canada is moving towards. So we have a need for higher performing windows than what a lot of the market has today. And this is really showing a snapshot of what most window manufacturers are producing today. This vertical line right here shows most typical dual pane insulated glass units are roughly about 3/4 of an inch wide. That's talking about just the glass itself. And the overall range that that glass can achieve with dual pane low E coatings with either argon or krypton, the surface 4 range that you can achieve, that's with that additional low E coating on the inside. That you can see the bump that you get with that 4th surface low E coating on there. And then the range that you can achieve with triple pane when you jump over triple pane. And you can see that this is really the direction that we need to move towards, is higher performing systems beyond what dual pane can really achieve. So that leads us to conventional triple pane glass. That looks something like this. If you look at just the glass itself, never mind the frame system that they're set within, they look something like this. We take typical dual pane glass and add another sheet, another spacer, and then an extra 3rd pane of glass on that. Now that does a great job. It gives us an extra layer of, or surface for an extra layer of low E coating on here. And because we have an extra air chamber in here, it really cuts down on those convective loops that we were talking about. So this does a phenomenal job. There are some drawbacks with conventional triple pane glass though. First off, it's almost twice as wide compared to a dual pane glass unit, which that requires a glazing pocket from the frame system that is almost twice as wide as well, or can accommodate that extra dimension. It's also, because it's triple pane, we have an extra sheet of glass on there as well. And because of that, it's almost twice as heavier as dual pane. In fact, that it's a little mistake on the slide right there. It's roughly 50% heavier than dual pane glass. And that added weight requires more robust frame systems to hold that extra weight. Same with the sashes and all the hardware, the operating hardware systems that go into these. It also requires additional labor on site to move the windows around, or even through shipping and extra handling, and sometimes requires additional equipment for installation for these as well. So all of that adds up to added cost, but when we start adding in more robust frames that can handle the extra weight. And this is a big reason why triple pane windows are many times more expensive than dual pane windows. It's not just because it's an extra sheet of glass. The extra sheet of glass doesn't add much to the overall cost of the assembly. It's the added weight and the extra glazing pocket that they require to get to that added performance. So we have a need in the market for lightweight, high-performing windows that are relatively thin, that can accommodate those thinner glazing pockets in the market. So now, how do we improve upon some of these systems? So we can always look at the low-hanging fruit, and that's the gas fill, the low E coatings that we already talked about, the IG spacers, the desiccants, the sealants, the glass. Those are a lot of the low-hanging fruit, and those are all very worthwhile considering. But we also have to consider some of the emerging codes when it comes to Energy Star standards. Where are we going from a code compliance to net zero to passive house? What standards are we building to? Along with other emerging carbon reduction standards, limits on greenhouse gases within existing buildings that we're starting to see in New York City. So taking a look at some of the easier ways to improve glazing systems, we could first take a look at the gas fill, and we still see some windows being filled with air, believe it or not, especially when we see windows being shipped in different elevations. So if they're being shipped from low elevation up to high elevation, we can't fill those or seal those because sealed air spaces will certainly go through some pressures in that elevation change. So we still see some windows being filled with air. You can see the density of that is there. Argon is an inert gas that is very common, and that's what most windows are being filled with within here. There is another inert gas called krypton right here, which is significantly more insulative than argon. It's not as readily available on the market. It does cost more, but the cost of that has recently come down. And so that is one method to really increase the overall performance of the glazing system. It is worth noting that there are optimal spaces, talking about the space that it's entered in, filled within, and its effectiveness in those various spaces right there. So argon is certainly better than air, and then krypton is then significantly much better than either of those first two. Another way to take a look at improving the thermal performance of glazing systems is the spacer system within the windows. And most commonly, you'll find metal spacer systems within here, and they're tried and true. This is the original spacer that was really put in within insulated glass windows, dating all the way back to the 1970s. So it's very, very common. And so what you'll find is various different shapes of metal spacers backed with a primary seal right here, and then backed up again by a secondary seal. Now, what happens on these is that if you have a very high performing insulated glass and argon gas and low E coatings, you can see that the center of glass performs very well, but the edge of glass is still relatively warm. This is viewed from the outside, where a lot of energy is still coming through through the edge, and those edges can account for about 10% of the overall area of the window. So that's one way to improve, is to take a look at the spacers. One alternate spacer system is called the warm edge spacer, and these are spacers that can be built of many different materials, non-metal materials. So these can be ranged from different types of polymers or plastics, all the way to foam spacers as well, that don't conduct heat as well as those metal spacer counterparts would. Or you can kind of see what a side-by-side comparison showing metal spacers on the left and warm edge spacers on the right-hand side, how much conductivity happens between those. Now, there is, of those two systems, they really employ the same basic components. We have a solid spacer right here with a primary seal and a secondary seal. Now, many times the problems with windows that we see all over the place, is insulated glass windows, is they fog up, and that's an indication that the seals have gone past their useful life. And what happens is with these spacer systems is through the heat and cold fluctuations of the year, that sealed airspace can experience several different pressures. In the wintertime, these seals, that primary seal, can experience a pinching effect. And then during the summertime, you can see a pulling effect at those seals. Over 20 or 30 years, you'll see that eventually go and release that seal, and that's when we see the fogging. And it's at that time that owners will start to consider, maybe we need new windows at that time because the seals have gone and they start thinking about replacing the windows. So what if we had a longer lasting seal? And that's what you'd find with a thermoplastic spacer, or TPS, otherwise sometimes known in the industry. It takes a different approach. Rather than this multi-point system right here, it injects more of a structural sealant within as the primary seal and backs it up with a secondary sealant behind there. And that TPS spacer also chemically bonds to the glass itself and the secondary spacer, producing a very long-lasting seal, adding more life to our windows and doors. Thermally, this performs about basically the same exact as the warm edge spacer that we saw in the previous slides. Now, if we want to look at more advanced systems, more emerging high-performance glazing systems, there are new technologies coming on the market that we'll cover in the next few slides that do give you the low, lightweight solution and overall thin dimension that can be used in many different window systems on the market. The first of which is thin glass. Now, this is the same type of glass that you see on your flat screen TVs, on a lot of your computer monitors, or even your cell phones. And this is not a new technology. This is actually a concept that was developed by the Berkeley National Laboratories back in the late 80s, before thin glass even existed. And really what it does is take a very thin sheet of glass and inserts it within a standard dual pane insulated glass right here, creating a thin triple right here. So this thin glass can range from 2 millimeters thick all the way down to 0.5 millimeter thick on this. And so now we have the opportunity to add additional layers of low E coatings on these. And so this can be produced as a thin triple, or what you see in the center of your screen, or even a thin quad window. And you can see that this can be used as glass within high performance windows. It can also be used as a secondary window. So think of this as an interior storm window is another way that this is being deployed. Now, thin glass is really just very much like a regular glass. It can be made a couple different ways, such as, like regular float glass, which is commonly referred to as soda lime float glass. There's a different manufacturing process for thin glass, which is a vertical fusion drawn, where molten glass is poured into this isopipe and then it spills out both sides. And as they drop down vertically, those two sheets fuse together, and as it drops vertically, it cools at the same time. It's cut, it's put off to the side, and then manufactured into whatever it needs to be. This is really how it gets to be so thin, very, very thin. So to recap, thin glass technologies, here's an example of quad, thin glass quads right here. Can be used in several different applications, from really just replacing existing glass in window systems. It's being used in new window systems, and it can also be used as a secondary window system. Your performance range ranges all the way from an R7 all the way up to that's for a thin triple. And when you start looking at thin quads, that can all get all the way up to an R16 center of glass performance value. The cost of this is going to be more than dual pane. It does perform significantly higher than dual pane, and it has more of a range than traditional thick triple pane glass. But because flat screen TVs, thin glass has been on the market for many, many years, so the scale up period has already happened today. And we can see overall dimensions, we're talking about the IGU right here. Dimensions range from 3/4 of an inch for a thin triple, all the way up to 2 inches for the wider thin quads on those. So big range for what those can happen. Now, vacuum insulated glass is a relatively newer option as well. So just like the thin glass, vacuum insulated glass has been a concept that's been around for over 50 years. And this is really using one of the best insulators on the market, which is a vacuum, because heat cannot travel through a vacuum on here. So the challenge has always been, how do we get this to seal on these? Because now we can't use traditional edge seals like we saw in conventional dual or triple, or even the thin triples and quads. This seal is under extreme stress because of the vacuum insulated properties. They also employ a spacer all throughout, or these pillars all throughout the assembly, to keep the 2 sheets of tempered glass from caving in on each other. And so you can see the edge of this, the profile of it is very, very thin, starting at just over 8 millimeters thick, front to back on these. So very, very thin system here. It's great solution to replace existing single pane systems on the market. And what you'll see, because this is a vacuum, is a port where all that air is evacuated out of it and then plugged at the port. So each of these vacuum insulated glass would have this port at the perimeter somewhere. Now, these spacers are a big subject to analyze very closely. These spacers can be made of several different materials. Polymers are ranging from polymers to a glass frit to metallic edge seals, right here. Each of those have their own different life expectancy, with the metallic edge seals really performing the best on those. And it's really a factor of how thick dimensionally, how thick that metallic spacer is. The thinner dimension it is, the less likely it is to perform long term. And so here's an example of one use of the vacuum insulated glass. This is the Tiffany & Company building in New York City, where all the existing single pane windows were set within stainless steel frames all throughout. They did not want to replace those stainless steel frames. They were very expensive to replace. So the owners opted to have them replaced with vacuum insulated glass because of that thin profile. Now, these are not the thermographic images that you see on the right-hand side. These are not that building, but you can kind of see what kind of a performance you get before as single pane glass and after, shown at the bottom. And what you'll still notice is the perimeter of these, because they're metal, the perimeters still don't perform as well, even though the rest of the center of glass performs exceptionally well. In addition, vacuum insulated glass can be employed along with kind of more of a hybrid scenario. So you have your typical vacuum insulated glass on the left, and then that's married with an extra sheet of glass to create an extremely high performing glass assembly, like what you see here, all the way up to an ranging from an R18 to roughly an R21. Extremely high, especially if we're considering many of the dual pane systems top out about an R4 for comparison. So in summary right here, vacuum insulated glass can be used in many different applications, from retrofit to new windows and also secondary windows. We've seen this being used in historic applications as the interior layer to add performance to that historic window. Performance range is very similar. Actually, we can top out a little bit higher than what we saw with thin glass, and starting baseline is about the same. Overall cost is going to be higher than that thin glass that we saw earlier, and these are rapidly scaling up, but we still see these going through that scale-up period today. And finally, aerogels are another option that we are seeing, able to get to that lightweight, high-performing goal that we have. And there is a company based in Waltham, Massachusetts, that is using aerogels. Now, aerogels are the lightest weight solid material being on Earth, and it's widely used throughout NASA because of its very high insulating properties. Now, one downside historically has been that aerogels have always had this translucent, semi-translucent appearance to it, sometimes with a bluish hue, but researchers have found ways to make it significantly more transparent, and now are marrying that aerogel to a sheet of glass. And this is really intended to fit within the same IGU pocket as a conventional dual pane glass, while keeping the overall weight low, and it can be glazed with argon or krypton gas fills, and low E coatings in addition to that. So this is a great substitute for dual pane insulated glass, just by adding that silica aerogel to the glass, reaching ultra efficiency. And one factor of this is it really depends, the efficiency really depends on the thickness of this material. So the thinner the material, the lower performing, and then vice versa. The thicker that material gets, the higher performing that can be. This is still in its infancy. We see this ramping up in scale in the next couple of years. I think even starting mass production starting next year as well. So to recap, in comparison, there's several different factors. Really what we're looking for are solutions that are available today to meet many of the standards, energy code standards that are coming online today as we reach towards electrification and affordability. And so here's a small snapshot of where conventional triple pane glass is as far as cost standpoint and overall center of glass performance values, just about ranging between R5, a little bit lower than R10. Your thin triples have a little bit higher range than conventional triples. That's due in large part by the seals and the gas fills that are being used with thin triples. And then your thin quads have a higher range, slightly higher price point along with that too. Now, your more other advanced systems, such as your vacuum insulated glass, alone is at a slightly higher, in a different price range, and then when it's married with a hybrid system, even higher performance range, but also higher price along with that too. Aerogels, we see these at a higher price and similar performance, just above the thin triples on those as well. So now it's not always about cost. There's many other considerations to consider. Optimal performance for your project, the overall durability of the systems, the technical ability that the manufacturers have of producing those systems, availability, acquisition cost, installation costs, and many other risks that you may want to consider when thinking about some of these systems. And that covers most of our learning objectives today. So we talked about many of the insulated glass performance measurements and defined what is high performance. Talked about how we measure high performance, and understand the glazing to wall ratio and the overall impact that windows have on the overall performance of the window or of a wall system. And then finally evaluated some of those emerging high performance technologies that are coming on the market today and coming within the next couple of years. And that takes care of today's presentation. If anyone would like to learn more about any of these technologies, you can certainly reach out to me. My information is listed right there at the bottom, or you can also engage us directly at the company I work for is Alpen High Performance Products. We employ some of these systems that we talked about today. Feel free to visit our website anytime, shown right there at the center of the screen. And Keegan, I'm curious if we have any questions.
Yeah, Jared, great job. Couple questions in here. Have any of these high-performing lightweight technologies yet been used by residential window manufacturers?
Yes. In fact, the residential window market, I know the vacuum insulated glass, there is a residential window company that is employing that hybrid version that we saw for the vacuum insulated glass. And my company, the Alpen High Performance, takes advantage of those thin glass options that we saw earlier in the slides.
You mentioned, or your bio mentioned, historic preservation projects. Could you talk, I know we only have a couple minutes left, I'm sure you could do a whole session on this alone, but just talk a little bit about window options when there are historic requirements that need to be met, external aesthetics and things like that that factor in.
Yeah, that's a big struggle right now with trying to balance the two between historic preservation guidelines that many times require or would prefer to see the existing windows stay in place and be maintained long term. So depending on the historic preservation commission that we're working with, sometimes they'll allow for window replacement, but when that's not the case, some of these options that we talked about through this presentation are secondary window systems. And so that would mean an interior storm window, and so that could look like the vacuum insulated glass I have seen be applied to the interior of, for example, leaded glass, where it was existing leaded glass, and so it's applied to the interior. Same with the thin glass options as well. My company has a thin glass interior storm for that as well. There's always questions about condensation for that, and that's always very case by case on how that condensation is actually handled on the inside. Beyond that, so we talked about lightweight, thin dimension. There are some other window companies out there who do a phenomenal job of making historic looking windows, but in modern assemblies. And so when those are used, we have a couple different options. We could look at if any of these options can be used in those chassis, window chassis, from a dimensional standpoint, and if they meet historic approval from there, or if there's some sort of a combination system where we can have a single pane window with, again, these secondary window systems put to the interior. Invariably, it's a case-by-case solution, and what the preservation team will allow and how that's balanced with the energy codes.
Great, and I think just a quick, we have time for one more. You touched on it a bit, but just solar heat gain coefficient. Good in the wintertime, not so good in the summertime, or solar gain. That is, where's the sweet spot? What's kind of the takeaway folks should think about when it comes to solar heat gain coefficient?
Yeah. There is no one performance value. It's very dependent on many factors. Really the climate zone that we're building in. Even in our climate zone 5 right here, we do see some situations where on modern homes that have a lot of glass, where you can almost get this fishbowl effect where too much heat gain can be too much. So what I would recommend is really engage your HERS raters or your energy modelers to find what is going to be best for each specific project. Lean on them early on the process, and they should be able to guide you to what's going to be best for the energy efficiency of the building, but also the occupant comfort for the people living in these spaces. I hate to dodge the question, but there's
it's a bit more nuanced, I think, than just
it is. Yeah. The earlier you can engage your professionals on the market, the better.
Great. Well, I think that's it for questions, and I know we're a couple minutes over our scheduled time, but Jared, thanks so much for sharing your expertise with us today. I encourage folks to reach out to you directly if they have other questions, and a reminder that the recording of this will be made available on the Mass Save YouTube channel. So thanks, Jared. Happy holidays, and hope to hear from you soon.
Thanks so much. Happy holidays, everyone.